We've been discussing the tree problem, and today, we went over it formally how to do it. Today I want to give you a more intuitive approach about how to solve the tree problem. Here is the function we were using that explains the growth in the value of the trees. It was equal to 1,000 times e to the square root of t power. We're assuming that the market interest rate is continuously compounded and is equal to r. Okay. The growth in the value of the trees, the growth rate in the value of the trees, let us denote that by r sub v. Let r sub v be this, 1 over v times dvdt. And this is the growth rate. It's the instantaneous growth rate in the value of the trees. This holds more generally. If you want the growth rate of variable y, the growth rate of variable y is just 1 over y times dy dt. In this case, our dependent variable is not y, it's v, but it's still the same thing. So this form right here gives you the growth rate. You can see that intuitively. DVDT is just the derivative of v with respect to time. The change in v with respect to time at a point. Now, if you just multiply that by 1 over v, then what you have in the numerator is dv over v dt. And dv over v is just the proportional change in v. So if you just take dv dt, multiply it by 1 over v, then you have the growth rate of v. Okay. An alternative expression for this is this. The growth rate in v is also equal to this, d log v dt. If you take the derivative of log v with respect to time, that is just 1 over v times dv dt. So it's an equivalent way of expressing the growth rate. Okay. Let's find the growth rate in the value of the trees. What this will measure is the proportional change in the value of the trees at a point in time. Rewriting this as 1,000 times e to the t to the 0.5 power, and we'll make it a little easier to get. And what is dv dt? Just the derivative, dv dt. Anybody? Hal, what would dv dt be? Okay, let's just review that. If you have, take this case here, say y is equal to e to the f of t power. In this case, what is dy dt? Yeah, Hal? What you do is you just take the derivative of the exponent, which is f prime of t, times e to the f of t. So in this case, f of t is just t to the 0.5. So Hal, what would this dv dt be then?
500t.
Right. What is f prime of t?
0.5t.
Yeah, it's point f prime. In this case, if you let f of t be e to the t to the 0.5 power, and f prime of t is just equal to, oh, I'm sorry, you let f of t be this, sorry. So it's e to the f of t. Let me back up. Suppose we have e to the f of t. Then if you let f of t be t to the 0.5, then f prime of t is just 0.5 t to the minus 0.5. Okay. Now, that's multiplied times the 1,000. So that's why Hal said 500. Hal, go ahead. The rest of it is?
T to the negative 0.5.
Right.
T to the T to the 1,500.
Right. Okay. So that's DVDT. Notice if you multiply this by 1 over v, we get the growth rate in v. And we just take this. Over v, and v is this thing right here. So v is, we put this down here. Okay. So it's 500 over 1,000, or 0.5, times, notice this cancels out, t to the minus 0.5. So this expression right here is the growth rate in the value of the trees. Okay. The growth rate in the value of the trees at any point in time. Notice we could rewrite this as 0.5 divided by the square root of t. T to the 0.5, if you bring that down to the denominator, is just the square root of t. So if we graph this, you could see what it looks like. Here's t. Here's the growth rate of v. And since you have the square root of t in the denominator, it's just going to have that shape right there. Obviously, as t goes to infinity, this denominator goes to infinity, so the growth rate goes to 0. If t goes to 0, then the growth rate approaches infinity. So if you graph it, the graph is asymptotically approaching the vertical axis as t approaches 0. Okay. And it asymptotically approaches the horizontal axis as t goes to infinity. It's always declining. As t gets bigger, obviously the denominator gets bigger, so it's always declining. So that's the growth rate and the value of the trees. Now, the optimal time to cut down the trees is when the growth rate and the value is just equal to the market interest rate. Here, the market interest rate, let's assume R is the market interest rate, just 0.1. So here's our R value, and they intersect right here. And if you work out the math, where they intersect is at 25 years. So intuitively, this makes sense. If the trees are growing and appreciating in value, then you want to let them grow as long as the growth rate and the value of the trees exceeds the market interest rate. Because then you're getting a better return on your trees than you would if you sold the trees and invested the money at 10%. So as long as the trees are appreciating or growing at a rate above 10%, you let them grow. As soon as their growth rate reaches 10%, then you cut them down. Now, this gives the maximum present value because we're assuming that the growth rate is declining. And in this case, it's certainly the case. So if you let the trees grow for more than 25 years, then their growth rate is below the market interest rate. So you've gone too far. And you certainly don't want to let them grow less than 25 because then they're appreciating by more than the market interest rate. So this is the intuitive explanation for the optimal time to cut down the trees. Okay. And this applies to any durable asset which is appreciating over time. As long as it's appreciating at a rate that exceeds the market interest rate, you continue to hold the asset. And the optimal time to sell it is when the appreciation rate the growth rate in value is just equal to the market interest rate. You can also see from this picture, the lower the market interest rate, the longer you'd let the trees grow. Okay. If the interest rate were only 5%, then the optimal time would obviously be greater. If the market interest rate were 0.05, then the optimal time would be over here. Okay. The lower the interest rate, the longer you let the trees grow. Okay.